Good afternoon, everyone. You are welcome to this class. Today we are going to continue from where we stopped. Before we continue today, I would like to show everyone the design we'll be working on. All right. So this is the design we'll be working on, and you can see we are done with panel 1. We are done with panel 2. Today we are moving to panel 3. But again, what I want to do now is, if you look at the design very well, see that panel 3, panel 5, and panel 6, they are one-way spanning slab. So I will look for the critical slab to analyze and design. Then the outputs, I will use the outputs to cater for the less critical slab. Okay, it works that way. So the designs are going to be similar. The UDL here, the same UDL here, the same UDL here. So the difference is just the span. All right, check the span, they are different. So I'm going to use this one to cater for this and this. So whatever output we get from here, we use it to reinforce these two slabs. Okay, so now let's proceed. Now this is our calculation sheet. We'll call it call this one, let's say this is the slab. All right, this is the span, this is the 3225. Okay, this is our UDL as 40.52 kilonewton per meter run. Okay, so our moment is obtained from our formula. Moment formula is equal to WL square over 8. All right, this is the moment formula in this particular one-way slab. Okay, this is different from two-way slab that we obtain the moment coefficient from the BS code. Now in this case is a one-way slab. Okay, so we apply the moment formula direct. Now this is the same as M is equals to 0.125 multiplied by UDL 14.52 multiplied by 3.225 square. Okay, now this 0.125, 1 divided by 8 is 0.125. Okay, now the W is the UDL, which is 14.52. Then the L is 3.225 square. Because this one is in millimeters, this one is now in meters. Okay, so when you compute this, you are going to have 0.125 multiplied 14.52 multiplied by 3.225 square. This one will give me 18.88 kilonewton meter. All right, this is the same as 18.88 times 10 raised to power 6 Newton millimeters. Okay, it's the same step in all the design. Now we've gotten our moment. The next step is to look for the value of our K. All right, after getting your moment, the next step is always the same as others. All right, now the next step is to get your K, the value for your K. The value for your K is 18.88 times 10 raised to power 6 over FCU, still the same thing, as 20 multiplied by 1000 multiplied by, this one is 124, our D square. This one is less than or equal to 0.156. Okay, now you compute this. When you compute this, 18.88 exponential 6 divided by 20 multiplied by 1000 multiplied by 124 square. This one will give me 0.06, 0.061. This is less than 0.156. So we use the lesser value as before. Now the next step is to solve for the lever arm. LA equals to 0.5 plus square root of 0.25 minus our k, 0.061 over 0.9. Okay, which must be less than or equal to 0.95. All right, whichever is the lesser we use. Okay, so let's compute. And 5 plus square of 0.25 minus 0.06 divided by 0.9. So after solving, we now have this to be 0.93. You can see that this one is less than 0.95. All right, we use the lesser value. Okay, so our z is equals to 0.93 multiplied by 124. So if you multiply this, we're going to have 0.93 times 124. This one will give me 115.32 mm. Okay. What's our next step? Is to solve for AS. AS required, which is equals to 18.88 multiplied by 10 raised to the power 6 all over 0.95, which is a constant, multiplied by characteristic strength of steel 410 multiplied by Z 115.32. Right? We're going to have, after computing, 18.88 exponential 6 divided by 0.95 multiplied by 410 multiplied by 115.32. This one will give me 420.33 millimeters square. All right. Now, this is the area required for this structure to be safe. If you go to your BS code, okay, you go to your BS code, you look for an area, the area of steel that is closer to this. The area of steel that is closer to this is Y12 at 250 center to center, and the area will be 452 millimeters square. If you go to your BS code, it's there. So you now say provide Y12 mm diameter bar at 250 center to center. Now this is a slab reinforcement. We call this one bottom. All right, I'm going to place this reinforcement at the bottom because the tension is at the bottom. This is a sagging moment. All right, the tension is going to be at the bottom, so you reinforce this at the bottom. So you can as well provide Y12 at 300 center to center for the distribution of this particular slab. Okay, so we now use this one to cater for panel is it panel 3 now, panel 3 and panel 4, okay, or panel 5. So you now use this one to cater for all those ones. So there will be no need solving for panel 3 and panel 5, as the case may be, if I'm not mistaken. Yeah, there's no need solving for panel 5, panel 6, so panel 3. You use this reinforcement for panel 3, you use the same reinforcement for panel 5, alright? So if you check for deflection, definitely deflection will be satisfied. But if you still want us to go further, analyzing this structure, designing, checking for deflection, we can still do that. Okay. All right. That is it for today. Thank you and God bless. So if you want to know more about the complete design of this structure, you go to my YouTube channel. All right. Thank you and God bless.